What are some of the weaknesses that it has despite being so well confirmed?
Well, I think that there are two kinds of weaknesses in the standard model. And, let's be fair. Let me be super duper fair. Three kinds of weaknesses in the standard model of particle physics. Okay. One is that gravity is not complete yet. We have a theory of gravity, general relativity, that is very, very good, but and there's even a quantum theory of gravity which works, here in the solar system. As long as gravity is not that strong, we have quantum gravity, no problem. But we don't have a complete, finished, final theory of quantum gravity, so we don't completely understand black holes or the Big Bang or things like that. Now, usually physicists deal with this just by not including quantum gravity in the standard model of particle physics. Frank Wilczek has advocated for grouping them together and calling them, did I say quantum field theory? Not including gravity in the standard model of particle physics. Frank Wilczek says we should call them the core theory as sort of a version of the standard model that does include gravity. But still, you would like to understand gravity better than you do. The second problem is that there is empirically something very, very big that was not part of the standard model, namely dark matter in the universe. So, and maybe there's other hints from like astrophysics and whatever, that the standard model is not quite up to the task of explaining observational data from astronomy, right? It explains very well observational data from laboratories here on Earth, but out there in the universe, it's a slightly different story. So almost everyone believes, although we're not 100% sure, that you need to go beyond the standard model to account for dark matter in the universe. That's the second problem. And then the third problem is, even though the theory fits the data, it does so at the cost of a weird set of fine-tunings that we don't understand. By which I mean, the standard model has all these different fields in it, and these fields interact with each other in different ways. And those interactions are generally parameterized by some coupling constants. And most of the coupling constants are very well behaved. They're, like the fine structure constant of electromagnetism is approximately 10 to the minus 2. It's, slightly small number, but it's not crazy or anything like that. But then there's these other numbers, like the ratio of the mass of the Higgs boson to the Planck scale of quantum gravity. That's 10 to the minus 16. That's a weirdly small number. And the ratio of the vacuum energy, the energy in empty space, to the Planck scale to the fourth power is 10 to the minus 120 and something. That's a crazily small number. And we don't know why. There's other small numbers, like there's a parameter in the strong interactions that governs violations of a symmetry called CP. You've probably never heard of any of this, but there's a number that should be between 0 and pi, and we measure it as less than 10 to the minus 10, and nobody knows why. So there's these weird features of the standard model that in order to fit the data, you have to take numbers that you would have guessed would have been 1, 10 to the minus 1, 10 to the minus 2, and set them to much, much smaller values. Those kind of fine-tuning problems hint to most of us that there is physics beyond the standard model that helps us make sense of these problems, but we don't know what it is yet.
Yeah, just to see if I can categorize these maybe two types of weaknesses, would it be fair to say, and again, totally shoot me down when and if I'm wrong, that something like dark matter could be fit into the standard model without having to totally revise it or find deeper physics, whereas the issues with fine tuning, like you just mentioned, that we don't understand, do in fact point to there being some deeper physics?
Well, dark matter does not fit into the standard model. You can come close. There's a couple of candidates for dark matter that you could argue are part of the standard model, namely massive neutrinos or black holes from the early universe. But in both cases, the standard model as it is not up to the task. You need to modify the standard model in some way to either produce black holes in the early universe or to give neutrinos or to create a kind of neutrino that can be massive enough to be the dark matter. But as we understand it right now, all of the particles in the standard model have been ruled out as candidates for dark matter.